In this video, I'm going to talk about some elementary derivative rules, specifically the derivatives of powers of x and sine and cosine. Okay. If you are interested in the proofs of these rules, I will probably link the video of me proving the power rule and proving the derivative for sine and cosine below in the description, but I'm not going to include that in this video. Okay, so the first thing I'm going to tell you about is the power rule. And this is how we would take the derivative of something like x to the fifth, or the third root of x, or 1 over x. Okay, this is a theorem. And again, the proof is a separate video, but it is on my channel. You just search for a proof of power rule. The derivative, which we're going to denote with this derivative with respect to x of operator, the derivative of the nth power of x is equal to n times x to the n minus 1. Okay. Now, I'm going to demonstrate to you how you would, come to this naturally for, say, a function like x squared. But this is the rule. Okay, the derivative of x to the n is n x to the n minus 1. So the derivative of, say, x to the fifth is 5x to the fourth. We bring the power down and reduce the power by 1. And this will become a very familiar operation to you over the course of this class. Okay, I'm going to point out a couple other ones that you might not think of, like square root of x. Well, that's like taking the derivative of x to the 1/2 power. So what we can do, we can bring that power around the front, n x to the n minus 1. So 1/2 x to the 1/2 minus 1 is 1/2 minus 2/2 is negative 1/2. Okay. Derivative with respect to x of, let's say, 1 over x. Okay, what we're going to do, we're going to write this as power. We say this is x to the negative first power, and we'll do the same thing. We'll do this power rule thing. We'll bring down the negative 1. We'll decrease the power by 1. This is just how you take the derivative of just kind of straightforward powers of x. Okay. Now, no reason why this is true yet. You have no reason to believe me yet. I'm not going to prove this in general, but I am going to show you why the derivative of x squared is 2x. Okay. So I'm going to say that, okay, if f of x is equal to x squared, then f prime of x, which we said last time was a function that gave us the slope of f at any x value. That's going to be 2x. And the reason why is we defined f prime of x to be the limit as h approaches 0 of f of x plus h minus f of x divided by h, the limit of rise over run as run went towards 0. Okay, and I'm telling you, we're going to be able to use f of x equals x squared, plug in on that, cancel off h's, and show that f prime of x is equal to 2x. Okay, in this case, with f of x equaling x squared, this is equal to the limit as h approaches 0 of, okay, well, f squares the thing on the inside, so I'm going to square x plus h, minus f of x is x squared, divided by h. Next thing is going to be to work on this. Okay, when I square x plus h and I do FOIL, or I distribute, or whatever you call it, I'm going to get x squared. I'm going to get 2 times x times h, and I'm going to get h squared. And then I still have this minus x squared in the numerator, and I'm going to divide by h. Okay, now you can see that, okay, x squared and negative x squared are going to go to 0, right? And I'll have 2 times x times h plus h squared divided by h. So I'm going to factor out an h here. Okay, and then this is the limit of 0 of 2x plus h is going to equal 2x. Okay, this is how you would algebraically show that the derivative of x squared is 2x. Okay. I'm going to give you a little bit more evidence here in a second. All right, and this is going to be, I need to make sure I've got 9 squares visible. So let's say that's, I should probably start here. I'm going to draw the graph of x squared and do the best I can. I think that's 9, 3. Yeah, okay. Okay, so I'm going to draw you a picture and try to, convince you that the derivative of x squared is in fact 2x. Probably. Uh-oh, I'm definitely been out of shape there. All right. So what I'm going to do, I'm going to actually only try to graph the derivative of, f of x equals 6. I'm probably only going to attempt to graph the derivative from -2 to 2. And I'm not going to really try to quantify the slopes. I mean, you could zoom in and be like, okay, you could draw yourself a tangent line and extend it and count squares or something. And maybe that would be an okay thing to do. I see that this is not the perfect line, but I'm going to try to draw something that's tangent to it. Probably needs to go a little steeper than that. And it appears that when I, it's actually, it doesn't work if I do it like this. You could do this using a graphing calculator, using the dy/dx feature or something like that, but that's kind of beside the point. Here, it's pretty steep and negative. Okay, so I'm going to say it's maybe down here, and then over here, it's negative, but not as steep as it was here. Okay, so it's less negative over here. And then at x equals 0, it's flat, okay, meaning the derivative is 0. At x equals 1, the slope is positive. Okay, I can see it kind of drawing in a tangent line slope. And you see it kind of looks like it might have slope too, based on the way I drew, if I was hopeful. But then as I go to x equals 2, it is considerably steeper. So the derivative is getting more positive. Okay, and so you can see this could potentially be 2x. Either way, it's very believable. Okay. Full-blown proof in general relies on the binomial theorem, and it's algebraic, and you can check it out if you're interested. I think next I'm going to talk to you about the derivative of sine and cosine. All right, so I'm going to tell you that the derivative of sine of x is cosine of x, and the derivative of cosine of x is equal to negative sine of x. Okay, and I'm going to draw you some pictures of why this is true. Okay? Again, if you want to know the proof or like the actual reason why this is true, it has to do with addition properties of sine and cosine, and you can check out that video if you're interested. Okay, so I'm going to draw you the graph of y equals sine of x. And remember kind of what the graph of sine of x does. It kind of goes up and down. Maybe I'll give it a couple more over here too. And about like that. All right. This is y equals sine x. And then I could say that the derivative, which we sometimes would call dy dx, okay, I'm going to just kind of graph it right over here. And hopefully you'll see that this is looking like cosine x. All right, over here, the slope is negative. And it's kind of, it's doing the same thing that it's doing over here. And if you look, we've got a zero slope here and a zero slope there. And it's negative everywhere else. And this is as negative as the slope gets, okay? I'm not going to really make an attempt to say how negative it is, but I know that this is as negative as it gets because as I'm kind of going this way, the way it's curving means that the slope is actually getting closer to flat, which means closer to zero. So I'm going to say right here at x equals what looks like negative 2 squares to the left of 0. It's really probably negative pi. I'm going to say that the derivative is negative. Okay, that is not 2 squares over. So 1 square. Okay, then at 1 square to the left of the origin, I've got a flat tangent, and we know that corresponds to a 0 derivative. Okay, over here, the derivative is positive. And then you see what I'm saying? Like, this is starting to look like the graph of cosine. Over here, the derivative is 0. At 2 squares, the derivative is negative. And it's the same behavior that it was right here, which is important because I can say that this point and this point have the same y-coordinate. Okay, I don't know what it is, but I'm say it's pretty reasonable to assume it's going to be 1. Okay, again, a 0 slope, and then a positive slope, because I know it's going to keep going up like that. And again, it's going to go up the same way that it went right here, so this height will be the same as that one. Okay. And we know that this looks like the graph of cosine because we know that cosine is the one that starts up at the top. Okay. And we see that dy dx is equal to cosine x. Okay. Now, what I'll tell you is there's going to be times in this class where we're going to want to take the derivative of the derivative. And we'll call that the second derivative. Okay, so we'll sometimes call that, like f double prime of x. If we talk about doing d dx to dy dx, symbolically, we actually write that like this. Second derivative of y with respect to x both times. Okay. And when I say it like that, you might be like, well, what else would you take it with respect to both times? But in a multivariable case, you could take a second derivative with respect to different variables in different contexts. Okay. And that's about all you need to be familiar with, I think, for the second derivative. It's all the notations we use for it. And then we're also interested in higher order derivatives in this, especially in the BC course later on. When we look at Taylor series, we're interested in really high order derivatives. And so I'll just say that the nth derivative will denote with f's nth. And after about 3, it becomes hard to count the number of tick marks. So we would just put a parenthesis and a number in there. In older textbooks, sometimes you would see a Roman numeral there also. But we would just put, like, the 5th derivative, we would just put parenthesis 5. Or the nth derivative of y with respect to x all n times. Okay, that's just notationally what we're going to do. And rather than drawing you a fresh new picture of cosine of x to take the derivative of, I figured I'd just tell you about the second derivative, and we'll decide to talk about the second derivative of sine, which would be the derivative of cosine, which I am proposing is negative sine. Okay, So I'm going to go over here, and this is going to be a graph of, oh, whoops, that's more y than I need. This is going to be the graph of the second derivative of y with respect to x both times if y is equal to sine x. All right, so over here at x equals -2, the slope of cosine is 0. -2 squares, excuse me, which we know is actually 1 pi. Each square is representing pi over 2 radians. And then over here, the slope is 1, or positive, excuse me. Over here, the slope is 0. The slope is negative. Slope is 0. Slope is positive. Slope is 0. And if you look, what is that? That is negative sine. Right? It starts at the origin but goes down. That's what negative sine does. Okay. Again, if you're interested in the algebraic reason why this holds, it has to do with kind of some trig addition, angle addition properties. And you can check that out if you're interested. Okay, so now I think I'm going to just work some examples. Okay, now the first example I've got for you is actually, I'm going to make another point, but f of x is equal to the cube root of x. Find f prime of -8. Okay, so we want to find the derivative of f, and we want to plug in x equals -8. That's the plan. Okay, so the first thing is we need to write this as a power of x, so we can use our new power rule. That's x to the 1/3 power. Okay. So what we need to do first is we need to find a formula for f prime of x. And oftentimes on free response type questions where they ask you for a derivative at a value, the first point is for the formula for the derivative, and the second point is for the answer. It's important that we write down our derivative formula first. Okay, so that's 1/3 x to the 1/3 minus 1 is 1/3 minus 3/3 is -2/3. Okay. Meaning that f prime of -8 is equal to 1/3 of -8 to the -2/3. All right, now if you are confident, you can say, okay, -8 to the -2/3 is going to be, well, 8 to the 2/3 is 4, because it's the cube root of 8 squared. Okay. And it's to the -2/3, so it's going to be 1/4. Be -1/4 is -1/12. But that's risky. I could have made an arithmetic error there. You could make an arithmetic error along the way. I would recommend you just leave it like that. Okay, because this is a numeric answer that's equivalent to any sort of other correct solution. All right. And then I could ask you, where is f not differentiable? Okay. You may remember from the last lesson or something, I mentioned that y equals the cube root of x. That has a vertical tangent at x equals 0. So I'm going to show you why that happens. Okay, I've got f prime of x is equal to 1/3 x to the -2/3. Well, what that really is f prime of x is equal to 1/3, and then x to the -2/3 is like x to the 2/3 in the denominator, which is x squared cubed rooted. And now you can see if I put in 0 for x here, that's going to cause a 0 denominator, and that's going to be undefined. And specifically, the closer we get to dividing by 0 here, the bigger this derivative is going to get. And that's why it makes sense that our slope is going towards infinity, right? Because we're getting closer and closer to taking 1 divided by 0. Okay. F prime does not exist at x equals 0. Okay, so I just wanted to connect that to the vertical tangent example and show you how that actually manifested itself within the algebra. All right. This is something that I'm not sure if it does or doesn't appear on the homework tonight, but this type of question is definitely something we'll see. And we don't really have, we have no way to deal with division, taking the derivative of a fraction or a quotient. We'll learn about that next time. Okay, but we can write this as, as powers of x just by distributing this 1 over x, or dividing through both things, or the heart-shaped thing, whatever you call it. Okay, so what we need to do is we need to rewrite g of x as 1 over x times x to the 4 minus 1. And so you may also see ones that are multiplication, where it's like where you need to distribute before taking the derivative. I'm pretty sure that's something that you will see on the homework this time. But what we're going to do is we're going to multiply 1 over x by x to the 4th. That's going to be x to the 3rd. And then by the negative 1, and that's minus x to the negative 1. Okay? And this is something that we can pretty easily take the derivative of. G prime of x is going to be, okay, I bring the power down, reduce the power by 1. Okay. And then over here, okay, bring this power down, multiply negative 1 by negative 1, I'm going to get plus x to the negative 2. Okay. I'm taking the derivative so that I can get the slope of the tangent line, and it should be easy enough to get a point because I know the x coordinate and I've got the the formula for the y coordinate of g, so it shouldn't be too tough. So g prime of negative 1 is going to be 3 times negative 1 squared is 3 times 1 plus negative 1 to the negative 2 power is that, right? Which is also going to be another 1, so 3 plus 1 is equal to 4. Okay, so I've got my slope of my tangent line. I think at this point I've mentioned to you that if we're going to write an equation for a tangent line, we want to use point-slope form. Okay, remember that point-slope form is y minus y0 is slope times x minus x0. So that's just what I recommend you do for the tangent line. You don't need to solve y equals mx plus b. You don't need to do that in this class. Very unnecessary. Just leads to unnecessary errors. So what we need to do is, in order to get our x naught, y naught, our point of tangency, we need to plug in x equals negative 1 to the formula for g. G of negative 1 is negative 1 to the 4th is 1 minus 1 is 0 over negative 1 is 0. Okay. So that means that my point is negative 1, 0. My slope is 4. And if I've got a point and slope, I can write an equation. Y minus 0 is equal to 4 times x minus negative 1. And in general, that's going to be how we write an equation for a tangent line. We get the derivative, we plug in the x value at the point of tangency, we nail down the point of tangency, and then we go point-slope equation. Alright, so this is a type of question, and I think I did not copy the full, I did not copy the full question. This is when x is less than or equal to 2, and this is when x is greater than 2. All right, we want to find the values of a and b that make the function differentiable. So this is very similar to the problem that we just did recently, where we found the values of a and b that made the function continuous. Okay, what often happened when we did that was we had like, a line and a parabola or something, and they met up at a sharp corner. So it would be continuous, but not differentiable. But now that we have a power rule, we're going to be able to make them not only meet up in the same place, but meet up smoothly. That's my best effort at showing you. So what we're going to need to do is we're going to need to match up the values of f of x, and we're going to need to match up the values of f prime of x. Okay, now before I go in and completely dive in on this, there's a couple things I need to tell you. First, I need to talk about the derivative of a number. Okay. Firstly, I'm going to just propose down here that the derivative of a constant is 0. Okay. And you may have already seen this in the previous lesson if you tried to take the derivative of something that was a flat line. Okay, because you saw it had zero slope. And if you think about y equals 5, well, that's a flat line that will have zero slope. So now, there's a couple of ways that I want you to think about this. Remember, the derivative is the rate of change. In constant, the word constant means not changing. Okay? So it's not surprised, there shouldn't be a big surprise to you that the derivative of a constant, something that does not change, the rate of change of something that's unchanging, would be 0. Okay? Also, I'm going to say that, you know, I've got something like 1. I could write that as x to the 0. Which is 0x to the negative 1, okay, which is 0. Okay, that's another way of thinking about it. And then, lastly, what I described earlier was, you know, if I have a graph of some function y is equal to a constant, like y equals 10. This is a flat line with no slope. Okay? The slope of this line is always 0. Okay, so the derivative of 10 is 0. Okay, so I'm just telling you that the derivative of a constant is 0. That's going to be a relevant enough fact in this class. I'm going to just like throw a nice little cloud around it. All right? And then the second thing I wanted to tell you was that if you want to take the derivative of a piecewise defined function, it's going to be equal to the derivatives of the respective pieces on their respective domain. Maybe not including the edge point. Okay. Now, we're going to say that it is going to need to include the edge point because we want the derivative to be, to meet up in the same way that the graph of f meets up to be continuous. So I'm going to just write down that f prime of x is equal to, all right, well, the derivative of a times x, okay, this is ax to the first. So what we would do is we would bring down that 1, multiply it by a. So it's a times 1 times x to the 0. Well, x to the 0 is 1. But this should make sense because we know that the line ax plus 5 is a line with slope a and y-intercept 5. So, and the derivative being the slope of the curve is it's going to be a everywhere. So for x less than 2. And then we know how to take the derivative of this now. We're going to bring the power down, multiply. 3 times 2 is 6. X to the 1 plus b, well, the derivative of b is going to be 0 because b is a constant. Okay, so it's 6x, where x is bigger than 2. Okay. So the two equations that we need to be true, or we need these two things to equal at x equals 2, and we need these two things to equal at x equals 2. So ax plus 5 equals 3x squared plus b at x equals 2. That's once I plug in x, I'm going to have a and b, so I'm going to need a little more information. So I'm going to need to work on this first. And I need a equal to 6x at x equals 2. And that's more like it. A is going to equal 6 times 2 is 12. And then I've got, okay, a is 12 times x is 2 plus 5 is equal to 3 times x squared is 4 plus b. Okay, so this is 24 and 5 is 29. It's equal to 12 plus b, and b is equal to 17. So I've got a equals 12 and b equals 17. You can't see that, but I was just clearly displaying the answer. I think I'll have one more example for you. Alright, so I think I'm just going to do a couple problems from the homework. This one is saying, find me the equation of the line or lines that are tangent to y equals x to the third plus 4x plus 1, and parallel to the line y minus 2 is 16 times x minus 3. So basically what we need here, what we need to pull out of this is the slope. Okay? And so really what we're hoping to find is the places where the slope of this curve is equal to 16, and then write the equations of the lines tangent to the curve that have that slope of 16. Okay, so really the only thing that this was giving to us was that 16. Okay, anyway, dy dx is going to be, okay, you multiply the power, reduce the power by 1. Okay, 3x to the 2 plus 4x to the 0 plus 0. Okay, so I need this slope to equal 16. So I'm going to find that that's going to happen at the places where 3 times x squared is equal to 12, which is where x squared is equal to 4, meaning x is either equal to 2 or x is equal to negative 2. Okay. So what I'll do is I'll just check both of these and make sure that the slope of this curve is 16 at this point. And it's like, yeah, okay, definitely. And so what I'm going to do is I've got the slopes, and I've got the x coordinates of the points. I just need to find the y coordinates. So for x equals 2, that'll be y equals 2 to the third is 8, plus another 8, plus 1, which is looking like 17. Okay, y equals negative 2 to the third is negative 8. 4 times negative 2 is another negative 8, plus 1 is looking like negative 15. Okay, so I've got 2 points, both same slope, so my tangent lines to this that have slope 16 are y minus 17 is equal to 16 times x minus positive 2, and y minus negative 15 is equal to 16 times x minus negative 2. And I'm just going to choose another one that looks kind of difficult, because you made it this far in the video. I think 13 is much the same. I think I'm going to do number 15. That one's actually pretty tough. So find the value of k for which the line y equals negative 2x plus 3 is tangent to y squared minus 2. All right, so I'm going to say, all right, if this is the line tangent, then the derivative is going to have to equal negative 2. That's something I know. Did they give us an x value? They did not. Okay. So I'm going to just say, well, the only thing I know is that if it's tangent there, the derivative at that point has to be negative 2. Okay. So over here I've got dy dx is equal to, all right, k is a constant, so 2 times k times x to the first minus 0. Okay. And that needs to equal negative 2, right? So it's got the same slope. All right, so I know that 2kx has to equal negative 2, and I'm really not sure what x is going to be, so I think I'm just going to hold on to that for now. I know that dy dx needs to equal dy dx, and I know that y needs to equal y if it's going to actually be tangent. So what I'm going to do is I'm going to say that negative 2x plus 3 is equal to kx squared minus 2. And now I really have a two-variable, two-equation system here, because I've got y equals y and dy dx equals dy dx. And I think the thing to do is going to be solve for k in this one and use substitution. This one's very tricky. So I'm going to start by dividing both sides by 2. Yeah, this seems right. Yeah, it really feels right here. Okay, so k is going to be negative 2 divided by 2 is negative 1 divided by x. Okay, and then I'm going to just throw this in over here, right? So I'm going to have negative 2x plus 3 equals k is negative 1 over x times x squared minus 2. So this is going to be another negative x. Yeah, here we go. This is something we're very good at solving, right? We're going to add 1, or maybe I'll just add 2 over here, and I'll get 1x, and I'll add over there, and I'll get 5. And I'll get k is negative 1/5. Okay, let me check on the answer key, because I think I've got an answer key to this homework, and make sure that that's right. I haven't done this problem in a long time. Yeah, k equals negative 1/5. Yeah, I think that's all I got for you for this video.